In today's video, we shall take a closer look at Newton's second law for rotation. We know that in the case of linear motion, if you have an object that is being acted upon by few forces, say 3 of them, so you have F1 and F2 acting to the right, and F3 is trying to push that object to the left. We know in this case the net force is given by F1 plus F2 minus F3. Now, of course, you can include the vector notation here. And that net force, by the definition of Newton's second law for linear motion, is quite simply m times the acceleration of that object, m being the mass of this object. So this is Newton's second law for linear motion. What about for rotation? Let's assume you have a pulley. You have a cord that is passing over the pulley on both sides like that, and you have objects connected to both sides. So these objects could have a different mass. Let's say the one on the left is 2 kg. The one on the right is, let's say, 3 kg. Assume this pulley spins about axis that is passing through the center, coming out of the board, in a clockwise direction as shown. So that means the 3 kg would go down, the 2 kg would go up with a certain acceleration. Let's for the moment ignore the presence of the two objects, at least in the picture, and see what's happening just to the pulley. The pulley has a radius of r, let's say, and it's rotating about the axis that is passing through the middle with an angular acceleration of alpha radian per second squared. How does the free body diagram for such a pulley look like? You have tension from the left-hand side cord in a downward direction, let's call it T left, and you also have tension on the right-hand side cord, downward direction, let's call it T sub r. This pulley is spinning with an angular acceleration. The question is, what is causing that angular acceleration? In the linear case, acceleration is caused by net force, as we have just seen a few minutes ago. So in this case, the angular acceleration is caused by a net torque. In our previous video, we did mention that angular acceleration is the rotational cousin of the linear acceleration, and likewise, the torque can be thought of as rotational cousin of that force. What that means is we should be able to relate the net torque to the angular acceleration of the system. So the net torque acting on the system is proportional to the angular acceleration of the system, just like net force acting on a mass is proportional to its acceleration for the linear case. However, for the rotational case, this proportionality, or the constant of proportionality, is the moment of inertia of that system. So there we have it. This is Newton's second law for rotation. And this equation can be applied for a system such as the one shown here, namely the pulley. So how do we calculate the net torque in this case? There are a couple of forces, and each of them would produce a torque. So the vector sum of these two torques will produce the net torque. So let's do one by one. Let's calculate the torque due to the left-hand side tension. Let's first do the direction. Remember, torque is defined as the vector r cross into the force. So in this case, the vector r extends from the axis of rotation to where the force acts, so in a leftward direction. And the force, as we have shown, is downward. If you were to curl your right hand fingers from the vector r to TL, your thumb would point out of the plane. So that is the direction of this torque, out of the plane. The magnitude of it is quite simple. It's the magnitude of that vector, in this case the same as the radius of that pulley, times the magnitude of that tension on the left-hand side. Now let's do the other contribution, the torque due to the right-hand side tension. The direction of that torque, again, is given by the cross product of two vectors, r times that tension on the right. The vector r in this case extends from the axis of rotation to where that force acts. So in this case it's rightward. The tension on the right is downward. So if you curl your right hand fingers from R to TR, your thumb will be going into the board. So there we have it. The second torque due to the right hand side tension is going into the board with a magnitude of R, that is the magnitude of that vector R, in this case the same as the radius of that pulley, times the tension on the right. So these two contributions have opposite signs. If this is minus, this one will be a plus. So the magnitude of the net torque in this case can be written as RTR minus RTL, because as we have said, the pulley is spinning clockwise, so this term dominates. Now we can equate this term to the moment of inertia of that pulley times the angular acceleration of that pulley, that one. So this is how we apply Newton's second law for rotation for rotational systems. It is less straightforward, especially when it comes to determining the direction of the net torque compared to the linear case. However, the algebra is exactly the same as for the linear case. Let's try to do this problem. A 4 kg block rests on frictionless horizontal surface. A string is attached to the block, passes over a pulley with radius 5 cm to a hanging block with mass 4 kg. When the system is released from rest, the blocks move 4 meters in 2 seconds. Find the tension in each part of the string and also the moment of inertia of the pulley. So what you have is a pulley like that and two blocks that is being connected to it in this manner. One block is resting on the horizontal surface and the other one is just hanging vertically. After the system is released, this pulley would turn like that and this block would go downward and the one that is resting on the horizontal surface would move rightward. That's the situation. The mass is 4 kg and 4 kg. Let's first look at the object that is resting on the horizontal surface. What is the free body diagram for such an object? Well, there is tension in this cord. I'm going to label it as T sub R. The direction of that tension acting on that 4 kg object is to the right. Of course, there is this weight, 4 times gravity, 4 being its mass, and then there is normal force acting like that from that horizontal surface onto that mass. And this normal force in this case is just equivalent to the weight. And then there is this acceleration, the linear acceleration. Newton's second law immediately tells us that the rightward tension is the one that is causing the acceleration of this object. So the net force is that TR, and that equals to mass times acceleration, so TR equals to 4 times A. So let's call this equation 1. Now let's look at the hanging object. So it is hanging downward and it's moving downward, so the forces would be the tension in that string. Let's call that tension TL, and then there is its weight, 4g, and the acceleration is the same as the first acceleration, namely A. Applying Newton's second law here, you see that the net force is downward, so the net force is 4g minus the tension TL, and that equals to 4 times A. So that is equation 2. Before we take a closer look at this pulley, let's look at the acceleration of the system. The acceleration, the linear acceleration A. Can we determine that acceleration? Well, based on the information that we are presented to us, we know that the blocks will move 4 meters in 2 seconds. So let's assume, so that is the distance it falls, 4 meters, and in 2 seconds it moves from rest, so 0 meter per second is the initial speed. So this is indeed kinematics because it's moving with constant acceleration. And in kinematics we can use that equation of kinematics to determine the acceleration. Because the initial speed is 0, that term will go away. It falls a distance of 4 meters, so s is 4, half a, and the time it takes is 2 seconds, so 2 squared. That means the acceleration turns out to be 2 meter per second squared. Another information that we will need. So based on this, we can determine part A, the tension in each part. So TR, the tension in that part of that string, is 4 times A being 2, so it is 8 newtons. TL, which is the tension here, can be determined from the second equation. So 4G minus TL equals 4A, A again being 2, so 4 times 2 is 8. And solving for TL, you get TL being 31.24 newtons. We have taken G to be 9.81 meter per second squared. Now let's look at part B, the moment of inertia of the pulley. Now we know the pulley is spinning clockwise with an angular acceleration alpha. The angular acceleration alpha can be determined from the acceleration that we have just determined, the linear acceleration. Because the radius of that pulley is 5 centimeters, we know that the linear acceleration equals that 5 centimeters, or in meters 0.05 meter, times the angular acceleration. So your angular acceleration turns out to be 40 radiant per second squared. Another information that will be useful in determining the moment of inertia of that pulley. Now let's look at the free body diagram of that pulley. Now it's being pulled by this tension to the left and this tension vertically downward. So there are 2 tensions, so this is the TR and this is the TL. These are the directions of these 2 tensions on the pulley. Let's calculate the torque. The torque due to TR equals to that radius of that pulley times the magnitude of TR. The direction of it, when you curl your right hand fingers from that vector to TR, thumb is pointing outward, so direction of that torque is outward. Now the direction of the torque due to TL. The vector R going rightward, so the magnitude is the radius of that pulley. Now when you curl from R to TL, your thumb is going into the board, so that torque is into the board with magnitude TL times R. Due to the motion, clockwise motion of the pulley, I'm going to take this to be the plus and this to be the minus. So the net torque acting on the pulley is TLR minus TRR, and that equals to the moment of inertia of the pulley times the angular acceleration. We know all the numbers except for the moment of inertia. TL is 31.24, TR is 8 times the radius, which is 5 cm, express that into meter, I times angular acceleration, which is 40. And you see you can determine the moment of inertia, which turns out to be 0.029 kg meter squared. And that's the answer for part B. And that solves the problem. Thank you for watching.